Hi class, in this video we're going to be talking about solving other types of equations. So up till now we've looked at solving linear equations, quadratic equations, but there are plenty of other types of equations that we're going to work with in precalculus and then later in calculus. And so it's important that we have some more strategies for the equations that aren't of those two very special forms. And so, right, if we think back to section 1.4 on quadratic equations, so 1.4 strategies only work for equations of the form ax squared plus bx plus c equal to 0. And so there will be plenty of other ones, like thinking back to even polynomials in the review video, that aren't of that strict form. And so we have 4 strategies that we're going to introduce today. 4 strategies. So we're going to talk about factor by grouping. And this is particularly useful for when working with polynomials. And then we're going to talk about how we solve rational equations. We're going to talk about how to solve radical equations and how we solve other special ones via substitution. So when we're looking at rational equations, we're going to have some sort of x over some other x. Or with radicals, we'll have, say, square roots or cubed roots, or we'll have fractional exponents. And so those are how we're going to handle those 2 types. But we'll start with solving by factoring, because that's actually very similar with factor by grouping, rather, is very similar to just straightforward factoring. So this first strategy is factor by grouping. And so if I have, for example, x cubed plus 2x squared minus x minus 2 equal to 0. So we can't just factor this into the product of 2 terms, because this isn't a quadratic. This is actually a trinomial, because we have up to a cubed. And so we can't just proceed directly into factoring it as we would. The first step we always want to do is we want to make one side 0. And so we already have one side equal to 0, so we don't have to do anything for this one. And now we're going to find factor common factors from groups. So what I mean by that is, instead of trying to factor out of everything, let's look at just this group of 2 and this group of 2. So here, this is an x cubed and a 2x squared, so each of them have an x squared as a factor. And so we can factor that out, and we're left with x plus 2. And then here, we can talk about where do we see maybe either, and so this is the thing we're always going to want to look for, is we're going to want to look for something that's common to both of our groups. So here, we have an x squared. Well, there's no x squared over there. Can we see an x plus 2? Well, I see minus x minus 2. So if I factor a negative 1 out, I'm left with x plus 2. And so notice now, we have an x plus 2 and an x plus 2. And so that we can factor out, x plus 2, and then we're left with an x squared, I'll get a third color, an x squared, and a minus 1. And so now, if this step was equal to 0, and this step is equal to 0, we have a term times another term equal to 0. So we're going to use our So factor common factors from groups, and then factor out something common to both. And then what we can do here is use our zero product principle. We know either that x plus 2 is equal to 0 or x squared minus 1 is equal to 0. Solving this one, we get x equals negative 2. Here we get x squared equals 1, or x equals plus or minus 1. Right? Remember, our square root always introduces a plus or minus. And then, after we do that, we check our solutions. So if I put a negative 2 in up here, I get negative 8 plus 8 is 0. Negative 2 is positive 2, minus 2 is 0. That whole term is 0, so that one is good. If I put in a positive 1, I get 1 plus 2 is 3, minus 1 is 2, minus 2 is 0, and our positive 1 is good. Negative 1, we have negative 1, and then we have plus 2, so we're at positive 1, minus the negative 1, we're at positive 2, minus 2, we're back at 0. So our solutions, and I like to add that step, is rewrite solutions. Our solutions are x equals negative 2, x equals 1, x equals negative 1. And so your question might be, what if I hadn't grouped it this way? What if I didn't group those, and instead I grouped those two and those two? Well, let's find out. So I'm going to rewrite that equation at the top of my next page. I have x cubed plus 2x squared minus x minus 2 is equal to 0. And I say, well, what if I had instead done it this way? X cubed minus x plus 2x squared minus 2. Still equal to 0. Well, if I group these two, I can now take an x out. X squared minus 1. And if I group these two, I can take a 2 out. Plus 2, x squared minus 1. So now what's common to both? My x squared minus 1, x squared minus 1. So x squared minus 1. I have an x plus 2, x plus 2 equals 0. And notice, x plus 2, x plus 2, x squared minus 1, x squared minus 1. We get the same terms. And since we get the same factors, we end up with the same result from our zero product principle and our same solutions. So let's go ahead and look at another example. 6x cubed minus 36x equals negative 2x squared plus 12. Just write my steps real quick over here. So we need one side 0. We need to factor the groups, and we need to factor overall. We need to use our zero product principle, and we need to check our solutions. And so first let's go ahead and get everything to the same side. So I'm going to add a 2x squared and subtract a 12 from both sides. 6x cubed minus 36x minus 2x squared plus 12 equals 0. And so in this case, again, we could group it two different ways. And so let me go ahead and account for both of those. So we could group it in this way, 6x cubed minus 36x minus 2x squared plus 12 equals 0. So that's a group, and that's a group. But we could also write it as 6x cubed minus 2x squared minus 36x plus 12 equal to 0, and group it into those two. So if we do this first one, each of these terms has a 6, and each of them have an x as a factor. So I'll take a 6x. I'm left with x squared minus 6. And then I look at this one, keeping in mind I'm going to want an x squared minus 6. And so we'll take a negative 2 out, so we're left with a positive x squared and a negative 6. Since we have this common to both, x squared minus 6 times 6x minus 2. Zero product principle says then that x squared minus 6 is equal to 0, or 6x minus 2 is equal to 0. This one on the right is a little bit easier. 6x equals 2, x equals 1/3. X squared equals 6 here on the left, so x equals plus or minus the square root of 6. Now in our last example up here, we got the same factors. So let's go ahead and proceed with this and see if we'll always get the same factors. So here we have 6x cubed minus 2x squared. Well, common to both is a 2 and an x squared, so 2x squared. So if I take a 2 out of that 6, I'm left with 3. If I take an x squared or x cubed, I'm left with x. Minus 2x squared, I'm left with just a minus 1. And then keeping in mind that I want a positive 3x minus 1, let's go ahead and take out a negative 12. And we're left with 3x minus 1 is equal to 0. And so now we have a 3x minus 1 common to both, 3x minus 1. And we have a 2x squared minus 12 left. Zero product principle, 3x minus 1 equals 0. 2x squared minus 12 equal to 0. Here we have 3x equals 1, or x equals 1/3. And then here on the other side we have 2x squared is equal to positive 12. Dividing by both sides by 2, we get x squared equals 6, so x equals plus or minus the square root of 6. And so notice, again, we have the same two solutions both ways. But now our factors, x squared minus 6 and 6x minus 2, are not the same as our factors here. And so how is that possible? Six x minus 2, is there another factor you could pull out of that? You could pull a 2, so let me go ahead, I'm going to move my paper up a little bit more and rewrite this. I could rewrite this as x squared minus 6 times 2 times 3x minus 1. So that equal to 0. And similarly here, this 2x squared and this 12 have a factor in common. So I could write that as 3x minus 1, 2x squared minus 6. Now what do you notice? That this and this are the same. And so zero product principle, we always talk about A and B. So there are only two products. Well, it really is generally true for any number of products. So if x squared minus 6 equals 0, we're going to get our plus or minus 6. 2 never equals 0, so we can just ignore that. So divide it from both sides. And 3x minus 1 is equal to 0. Gives us our third. And so what happens in each of those cases is because there's this extra factor of 2 that everything has in common in the original, it shows up in one of two places at the end. So what that also means is from this very original, you could have rewritten it as 3x cubed minus 18x minus x squared plus 6 equals 0. And when we would do factor by grouping on that, you would get x squared minus 6 and 3x minus 1. So that's factor by grouping. I think it's important to realize that you have choices in when you group. Some choices will make more sense than others, right? If I look at either one of these, say this one here, if I tried to do x cubed minus 2 plus 2x squared minus x equals 0, well, x cubed minus 2 doesn't have any factors common, and while this 2x squared minus x has an x common to both, 2x minus 1, x cubed minus 2, that doesn't make it any easier. So we always want to be intelligent, or at least plan how we're choosing our groups. We want to choose groups that have factors common to them, so that in our next step, both of our groups, after they've been factored, will also have a factor common. Sometimes it's trial and error. Just try putting pairs together and see if that leads you somewhere. If it doesn't, try another pair. And in other times, it doesn't actually matter where you end up pairing. I mean, I guess it does here, right? Even in all of these cases, you couldn't put 6x cubed and 12 together, because if you took a 2 out, you would have 3x cubed, or a 6 even. You would take a 6 out, you'd have x cubed plus 2, and that doesn't reduce, and we're not going to magically get an x cubed in our x squared term. So it's really important that we try to pick knowing where we're going, so that it kind of leads us there a little bit more quickly. All right, so that's factor by grouping. Our next process is called solving rational equations. And so that's something that looks like this: x plus 3 over x minus 1 plus x plus 4 over x plus 1 equals 8x plus 5 over x squared minus 1. Sorry, that's a little crooked. Let me see if I can fix that. There we go. Where we have x plus 3 over x minus 1 plus x plus 4 over x plus 1 equals 8x plus 5 over x squared minus 1. So our process for solving rational equations is we're always going to first start by finding the least common denominator. And so when we have our least common denominator, that's going to help us to simplify it. So if I look at my denominator, x squared minus 1, well, that's our special form. We have a square, a minus, and a square. So that's really x minus 1 times x plus 1. So here we have an x plus 1, and here we have an x minus 1. And so we need to make sure all of those end up with x minus 1 and x plus 1 in the denominator. But instead of actually writing it as a common denominator, or no, let's go ahead and we'll write our common denominator, and then we'll take the next step. So if I want x minus 1 times x plus 1 in this denominator, let me get a different color. So I had x minus 1, x plus 3. And since I want x minus 1, x plus 1, I need to do an x plus 1 on both the numerator and the denominator. Similarly here, plus, here we have x plus 1, x plus 4. And so this one is missing x minus 1. And we have to put on both the top and the bottom to not change the size of our fraction. And that is equal to 8x plus 5 over x minus 1, x plus 1. And we don't need to do anything to that denominator or numerator. And so our second step is multiply both sides by the LCD, least common denominator. And so, put some big parentheses around that. X minus 1, x plus 1, x minus 1, x plus 1. So this one divided by itself is just a 1. And then this one, it's important we remember to distribute it to both terms. And so that will cancel this denominator, and that will cancel this denominator, so that we're left with x plus 3, x plus 1, plus x plus 4, x minus 1, equals 8x plus 5. And now we can go ahead and work on distribution. X squared, x, 3x, 3, x squared minus x plus 4x minus 4 equals 8x plus 5. And then step 3, we want to make one side 0. And so I'll put all of my x squareds together, all my x's together, and all of my constants. So I have an x squared, that's taken care of, plus x, plus 3x. Oh, I have another x squared, minus x, plus 4x, and then, oh, I didn't subtract those over yet. So if I subtract that over, I get a minus 8x. That's taken care of. And then our constant terms, plus 3, minus 4, minus 5 equals 0. So I simplify and make one side 0. So let's go ahead and tackle each of these sets of terms. X squared plus x squared is 2x squared. Then we have x plus 3x is 4x, minus x is 3x, plus 4x is 7x, minus 8x, I think is minus 1. I lost track. So 1, 4, 3, 7, minus 1, negative x. 3 minus 4 is negative 1, minus 5 is negative 6, equals 0. And so from here, we need to try to solve. And so what we need to do to factor this is we need to look at factor pairs of 6. Whenever one of them is multiplied by 2, their product is negative 1. And so we know we're going to end up with a 2x and an x. And it turns out if I make this a negative 2 times 3, I get negative 6. And 2 times negative 2 is negative. So 2 times negative 2 plus 3 is negative 1. So we have 2x plus 3x minus 2 equal to 0. So step 4 is factor. Step 5 is our 0 product principle. So we know either that 2x plus 3 equals 0 or x minus 2 equals 0. Oh, you can't see. Let me slide that up a little bit. And here we can subtract the 3 over and divide by 2. X equals negative 3 halves, or x equals 2. And those are our solutions. And of course, our next step is to go back and we look at the original and make sure that we can indeed substitute both of those solutions. Something I didn't do, and we always should do when we're looking at rationals, is specify our domain. So here our domain, it's x can't be 1 and x can't be negative 1. Otherwise that would be 0 or that would be 0. So if one of those were our solutions, we could say, well, that's not a solution because our equation is undefined. But it turns out that neither of those are zeros of the denominator. And if you would say put a 2 in, we would have 2 plus 3 is 5, plus 6 over 3 is 2, so 5 plus 2 is 7. So here we have 24, 29. Is that right? 2, no. 16, we have 21 over 2 squared is 4 minus 1 is 3. 21 divided by 3 is 7. We have 7 equals 7. So that one works. You can check the other one, but it will also work. But let's look at another one of these. And so this is one of those things, just like factoring, the more you do this type of problem, the more comfortable you'll feel. So if we have an example, x over x plus 1 plus x plus 1 over x plus 2 equals 1. So just to write our steps real quick, so we find our LCD, we rewrite fractions, we multiply by the LCD, we factor, then use our zero product principle, and then we check our solutions. So our LCD needs to have an x plus 1 and an x plus 2 in it. And this in the denominator is really just 1 over 1. And so it also needs to have a 1. But when you multiply anything by 1, it doesn't change. So we'll rewrite that. Our fractions, so our least common denominator is x plus 1, x plus 2. So we already had x over x plus 1, so we need 2 of these x plus 2's, plus, and this one made x plus 1 over x plus 2, and it's missing an x plus 1. And so it doesn't matter that there's already an x plus 1 in the numerator. We can only do the same thing to both the numerator and the denominator to not change it. So that one has to go along for the ride. And then here, since there's only 1, we need both in the denominator, x plus 1, x plus 2, and so both get carried along to the numerator. And then step 2 was rewriting fractions. Check. Step 3, multiply by our LCD. X plus 1, x plus 2, x plus 1, x plus 2. So again, we distribute that through to cancel out both of those denominators. And then this one cancels the single denominator. We have x times x plus 2 plus x plus 1, x plus 1 equals x plus 1, x plus 2. And to factor, I need to get one of them equal to 0, so I'll move that over. X plus 2 plus x plus 1 times x plus 1 minus x plus 1 times x plus 2 equals 0. It's a lot, but let's go ahead and simplify. X squared plus 2x plus x squared plus x plus x plus 1 minus, and I'm going to use a square bracket so I don't lose track of that negative sign, x squared plus 2x plus x plus 2 equals 0. And so that negative is going to need to get distributed to each of those. But I'm going to also gather up my x squared terms. So I have an x squared, so that one's taken care of. Then we have another x squared. Then we have a minus x squared. So those are taken care of. Plus, now my x terms, 2x plus x plus x, negative 2x minus 2x, negative x. That's all my x terms. And then my constant terms, none here. We have a 1 minus 2 equals 0. So we can combine like terms, x squared, 2x squared, it's back down to 1x squared, 2x, 3x, 4x, 2x, 1x, minus 1 equals 0. And then from here, we need to see how to factor. And so if we try to factor this, we need two numbers whose product is -1. Well, that's got to be -1 and +1. But we need their sum to be +1. So -1 plus 1 is 0. So it doesn't factor. So instead of factor and zero product principle, we can use our quadratic formula. So A equals 1, B equals 1, C equals -1. And our quadratic formula tells us that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And so here we have -1 plus or minus the square root of 1 minus 4ac all over 2a. And so to simplify, we get -1 plus or minus the square root of 1, -4, -4, +4, 1 plus 4 over 2, which is -1 plus or minus the square root of 5 over 2. And those are our two solutions. And we can go back and check them, and if you substitute those into the original, you shall find out that they do, in fact, give us true statements. So rational equations, when they factor, like our previous example, particularly not bad. If we need to use quadratic formula, maybe a little bit more work, but nonetheless, we're able to get to our solution. So we have just a couple more examples. Solving radical equations. And so once we do this, if I could slide my clipboard the right way, that would be if we had something like this, the cubed root of 2x plus 3 equals 3. Or x plus the square root of x plus 6 is equal to 0. Or we might have something that looks like this, 2x minus 6 to the 2/3 plus 9 equals 13. Or even we could have something that has 2, 3q plus 1, the square root of that, minus the square root of q minus 1 is equal to 2. And so these are the four examples we're going to work through because each of them kind of proceeds slightly differently. Maybe the first two are actually very similar. But we'll go ahead and start with this first. Here we have the cubed root of 2x plus 3 is equal to 3. So our first step is to get a radical of 1. Isolate the radical is perhaps another way of saying the same thing. And when we do that, Well, this radical is already on the left-hand side by itself, and this 3 is fine on the other side. So to undo a cubed root, we cube it. So now we'll take the cubed root of 2x plus 3 to the third equals 3 to the third. And so now it might be worthwhile to remind us of some of our rules of exponents. Well, we have x to the half is the same as the square root. And x to the 3 halves is the same as this, not the square root of 2, the square root of x, is the same as the square root of x all to the third power. If we have some x to the 2/3, and then we raise that to the 3 halves, that's the same as x to the first, or just x. And we also have the x to some fractional power, a third, squared, is the same as x to the 2/3. So what this is reminding us is that this is really 2x plus 3 to the 1/3 to the third. And 3 times a third is just 1. So we're 2x plus 3 equals 3 times 3 is 9 times 3 is 27. 2x equals 24. X equals 12. So I didn't give you any of your other steps. So we isolate, get a radical alone. We eliminate. So that's isolate radical, eliminate radical, solve however you like, and then check our solutions. So if we look at that second example I have up there, x plus the square root of x plus 6 equals to 0. We need to isolate that radical first. So go ahead and subtract that x to the other side. We get the square root of x plus 6 equals negative x. To undo a square root, we square both sides. X plus 6 equals negative x times a negative x is always x squared, and it will always be positive. So now we have x squared minus x minus 6 equals 0. Can we factor it? X and x, so we need 6's factors, negative 6's factors that when added together give us negative 1. So that's 2 and negative 3. Equal to 0. Our zero product principle says that x plus 2 equals 0, or x minus 3 is equal to 0. So x is negative 2, or x is equal to 3. Check and check. To check it, we put negative 2 up here. Negative 2 plus 6 is 4. Square root of 4 is 2. Negative 2 plus 2 is 0. 3 plus the square root of 9 is 3. And so what does that mean? That doesn't give us a 0. So what we end up seeing is why we need to go back and check. Here we have x equals 3. And now think back to, was it the last video, where it was our square root always introduces a plus or minus. I have x plus the square root of x plus 6 equals to 0. If I substitute x equals 3 into that, I get 3 plus the square root of 9 equals 0. Well, what is the square root of 9? The square root of 9 is plus or minus 3. So 3 plus or minus 3 equals 0. Well, 3 plus 3 doesn't equal 0. 3 minus 3 does equal 0. So the algebra there, the calculation, does work out. Because 3 minus 3 is equal to 0. Now, eventually we'll talk about the special, that's a special kind of 0, because it only works for the negative case. But we can talk about x minus 3 being a solution. And we can talk about x equals 3. Wait, what did I say? We can talk about as x being negative 2 is unquestionably a solution, right? We have negative 2 plus the square root of 4 plus or minus 2. We're good. But because the 3, we have a 3 plus or minus 3, that will be a special kind of 0 that we'll come back to in a few videos from now. So this was like that first day we were like, let's work through. Oh, we can't solve it. We'll come back. Quadratic formula helped us there. So here we hit a special type of 0 where you can say, yeah, that works. It gives us a true statement, but we're going to revisit why it's special in a few videos. So I have 2 more examples of this kind, right? Those were 2x minus 6 to the 2/3 plus 9 equals 13. And let's see if I can use only half of a sheet of paper. We have 3q plus 1 minus q minus 1 equals 2. And so from here, what we have is we need to isolate our radical. So 2x minus 6 to the 2/3 equals 4. To undo a 2/3, we do a 3/2. So we have 2x minus 6 equals, and 3/2 is the same as the square root of 4 cubed. 2x minus 6 equals, if we have the square root of 4, we get plus or minus 2 cubed. 2x minus 6 equals, and then we'll go ahead and cube this. So a positive times positive, a positive is a positive, and negative times a negative is a negative. So we still get plus or minus 8. So add the 6 to both sides. 2x equals 6 plus or minus 8. We can go ahead, we can divide by 2 now, or we can simplify. So let's divide by 2. We'll get x equals 3 plus or minus 4. So x equals 3, or x plus 4 is 7. 3 minus 4 is negative 1. And we always need to check our answers. So if we have 2x minus 6 to the 2/3 plus 9 equals 13. Actually, I wish I would have taken the next step. 2x minus 6 to the 2/3 equals 4. If I plug in 7, I get 14 minus 8. 8 minus 6. 2/3. So that's the cubed root of 8 squared. Cube root of 8 is 2 squared. 4 equals 4. So we're good there. And we'll check our negative 1. So we're going to have 2 times negative 1 minus 6 to the 2/3. We want to see if that's equal to 4. Negative 2 minus 6 is negative 8. The cube root of that is negative 2. And we square that, we get 4. So check and check. So that wasn't so bad. And now this last example is important because there are 2 radicals. We have to isolate them. So let's get this with 3q plus 1 by itself. And then remember this had a minus in front of it. So we'll go ahead and do 2 plus the square root of q minus 1. And then to undo a radical, we square both sides. And so here we have 3q plus 1. But it's important to remember here when we square, it's not just as simple as squaring each of those. We have 2 plus the square root of q minus 1 times q, 2 plus the square root of q minus 1. So that tells us that 3q plus 1 is equal to 4 plus 2 and 4, so 4 square roots of q minus 1 plus, and then if we have q minus 1 root times the root of q minus 1, we're left with just what's on the inside, q minus 1. And now we need to go back to isolate the radical step. So let's go ahead and we'll take this term and these two to this side. So 3q minus 1q is 2q. 1 minus 4 is negative 3, plus 1 is negative 2, equals 4 root q minus 1. Now you can divide both sides by 4, or you can leave the 4 there, because it does, if you say isolate the radical, you can leave it that constant in front of it, and that won't affect it. We'll go ahead and square both sides. So this is 2q minus 2, 2q minus 2 equals 16, q minus 1. 2 times 2 is 4q squared minus 4q minus 4q plus 4 equals 16q minus 1. Oh, you couldn't quite see that because my clipboard's a little too far down. 4q squared, we have, that was taken care of, minus 4, minus 8, move that over, minus 16, minus 24q, 4 plus 1, nope, 16, 4 plus 16 is 20. We can take a 4 out of everything. So we have a q squared minus 6q plus 5 equals 0. And we need factors of 5 to add to negative 6. So we have q minus 1, q minus 5 equals 0. Q equals 1, or Q equals 5. So whenever we have 2 radicals, you have to repeat that process twice. And so to show you our general flow chart, so I gave you our other example our other chart where we isolate the radical, eliminate it, and then what you need to do after you do that is you might have to isolate the radical and eliminate it again. And you'll repeat that until you have no more radicals. And then you can move on to making a side 0, and then factor and use the zero product principle, or solve it some other way, completing the square, quadratic formula, and then checking your solutions at the end. So we have one more type of problem that we want to cover in today's video. And this type of problem is called factoring or solving via substitution. So let me get my black pen. Solving, but really it's factoring via substitution. And so what this is a process to get equations into the form a times u squared plus bu plus c equals 0. And now remember, this is a quadratic. It's our polynomial of degree 2 in standard form. But notice I used a u instead of x. It's because what we're going to do, so our process, is we're going to choose u so that the equation after substituting will be of the form, and this will make more sense once I do an example, au squared plus bu plus c equals 0. And then we'll solve for u using one of our strategies. And then we will solve for x. So consider this example. X to the 4th minus 7x squared plus 12 is equal to 0. Now we can't factor this using our standard process because that works when we have something in the form ax squared plus bx plus c equals to 0. And unfortunately, we can't use our standard factor by grouping method because we only have 3 terms, and we only introduced factor by grouping for when we had 4. It doesn't mean we can't use factor by grouping, but we'll talk about that another time. So we're going to say right, I need this to be a u and a u squared. Well, if I want this to be u, let u equal x squared. So if we rewrite our original x to the 4th minus 7x squared plus 12 equals 0 as u is x squared, so we have minus 7u plus 12. And if x squared is u, x to the 4th is u squared. U squared minus 7u plus 12. Well, now that's just our standard quadratic with a leading coefficient of 1. And so now we can factor. We need our factors of 12 that when multiplied together give us 12, but then when added together give us negative 7. So here we have u minus 4, u minus 3, because we'll get minus 3 minus 4 is negative 7, but multiplies 12. So zero product principle tells us that u equals 4 or u equals 3. But this is why my step 3 is solve for x. This says that u is 4 or u is 3. But u is x squared. So that means that x squared equals 4 or x squared equals 3. And then to solve that, we get x equals plus or minus 2, or x equals plus or minus the square root of 3. And so notice our solutions are x equals 2, x equals negative 2, x equals root 3, x equals negative root 3. So this equation has 4 possible solutions. And that became the case because our u was x squared. And so since u could be one of these two values, x can be any one of these 4 to still give us a true solution. Again, you can take this, plug it into your original. 2 to the 4th minus 7 times 2 squared. So we have 2, 4, 8, 16. 16 minus 7 times 4 is 28. Negative 12 plus 12 is 0. And that same will work for negative 2. And 3 will work, or root 3 will work as well, because we have 9 minus 21 plus 12, which is 0. So we always check our x's after we get to it. If we didn't have one that worked, we know we either messed up when we were solving for u, so we should recheck this work, or we made a mistake when we were solving for x, and we need to recheck that work. So there are 2 places we need to check. I'll give you just 2 more examples, and that will conclude today's video. We have x to the 2/5 plus x to the 1/5 minus 2 equals 0. Right? And remember, we need to pick our u so that we get something of the form au squared plus bu plus c equals 0. So here we let u equal x to the 1/5 because we want that term to be u. So x to the 1/5 squared, and that's why I gave us our reminder about exponents. X to the 1/3 squared is x to the 2/3. So u squared, if u is x to the 1/5, u squared is x to the 1/5 squared, or x to the 2/5, which is what we wanted here. U squared plus u minus 2 equals 0. So we need our factors of 2 that when multiplied give us negative 2, but when added give us positive 1. So here we have u minus 2, u plus 1 equals 0. I wrote those wrong, didn't I? U plus 2, u minus 1. I knew something was wrong. I wrote those numbers down instead of these ones. So we have u plus 2, u minus 1, which means that u equals 1, or u equals negative 2. Remember, we care about x. So that means x to the 1/5 equals 1, or x to the 1/5 equals negative 2. And if it's helpful, remember x to the 1/5 means the 5th root of x is 1, and the 5th root of x is negative 2. So to undo that, we raise both sides to the 5th power. If x equals 1, or x equals 2, 4, 8, 16, 32, and negative 1 times itself an odd number of times is negative. So x equals 1, or x equals negative 32. Those are our 2 solutions. You can go back and check those in the original. 1 plus 1 minus 2 is 0. 4 minus 2 is 0. They both check out. And then sometimes our u substitution is a little bit more involved. So look at this example. 2 root t plus 1 squared minus 2 root t plus 1 minus 3 is equal to 0. Well, we know we want au squared plus bu plus c equal to 0. And so we have let u equals 2 root t plus 1. u squared minus 2u minus 3 equals 0. We need our negative 3 times a positive 1. We get negative 3, negative 2. So we have u minus 3, u plus 1, u equals 3, u equals negative 1. But again, we need to solve for our variable, which in this case was t. So we have 3 equals 2 root t plus 1, or negative 1 equals 2 root t plus 1. Go ahead and subtract that 1 over. 2 equals 2 root t. Divide both sides by 2. Root t equals 1. Square both sides. T equals 1. Go ahead and subtract that over. We have negative 2 equals 2 root t. Root t equals negative 1. Square both sides. And we get t equals 1. Well, that's interesting. Both of our solutions, sorry, that was a little crooked there, are 1. And so just like when we had that special case where it was only a solution when the plus or minus 1 happened, we're going to have another special case when we get the same 0 for both. And I won't give you the name for that today. But we know that then our solution is t equals 1. So we get 2 times 1 plus 1, because 3 squared is 9, minus 6 minus 3 is 0. So it checks out. And so that gives us a way to handle at least 4 other kinds of equations. When we have polynomials greater than degree 2, we can use factor by grouping. When we have rational equations, so we have fractions with variables in the denominator, we have a process for finding the least common denominator and handling that. We have a process for handling radical equations, where we isolate the radical first before proceeding. But sometimes we have to repeat that process a couple times to get rid of all of them. And then our last is via substitution, where sometimes it's almost like a quadratic. It's not a quadratic directly, but via a substitution becomes equivalent to a quadratic. So, spend some time with these, and I think you'll be adequately prepared for your MATH homework. I'll see y'all next time.